All right, boys and girls, welcome back to the drive-through for it's getting really difficult to do these videos version. Brought to you by the deli. Hungry? Stop by the deli. It was my week. Oh yeah, it's the Leap Day edition of the drive-through. Sponsored by the deli. Hungry? Stop by the deli and get some fresh either honey oat loaf or fresh sourdough bread baked by the Wyoming Pastry Shop, fresh at the deli this week. All right, so hopefully you remember parametric curves. Okay. It's basically, we traced out, we call these vector valued functions, and we traced out the tips of these vectors over various times t, or variables t, where we let x equal f of t, y equal g of t, and z equal h of t. And remember, like, the most famous one was probably sine t cosine t t, and that gave us half of our double helix. Let me orientate it the right way. I think it would go like this. Okay, hopefully you remember that. Well, now we're doing parametric surface. Okay, so a parametric surface, instead of having a single variable t, will now look like this. R of u comma v is, and now we'll have functions, so we'll just write this, x of u comma v comma y of u comma v comma z of u comma v, meaning you got three different functions that are now functions of up to two variables, and the difference is that these parametric surfaces will now no longer give you lines, but they are a new way to describe a surface. Remember what a surface is. A surface is an infinitely thin layer of, let's say, skin, and that's something that we can find the area of or the volume inside of with some given bounds. Okay, so the first thing we'll do is we'll practice identifying and sketching. So our function is 3 cosine u, 3 sine u, v, or x equals 3 cosine u, y equals 3 sine of u, and z equals v. Okay, so that is a function of, those are functions of u and v, and that makes this a surface. So notice that x squared plus y squared equals 3 squared cosine squared u plus 3 squared sine squared u, which is equal to 9 times sine squared u plus cosine squared u, which is equal to 9 times 1, which is equal to 9. So we know that x squared plus y squared will always equal 9. So what that does is give us an idea that all points x and y on this surface will lie on the circle centered at 0, 0 with a radius 3. Not the best perspective there, but anyway. And then z goes from 0 to 4. So we know that u is going from 0 to 2 pi. V goes from 0 to 4. However, z equals v. So it's going to go up 1, 2, 3, 4. And now hopefully we can see that this surface is a cylinder that goes from 0 to 4 in the z direction, centered at the origin with a radius of 3. So keep in mind, this cylinder is hollow. Please remember that. Okay, and that's what the surface is. It is a layer of skin that forms a circular cylinder. Okay, let's try another one. Now, granted, when we do this method, the book even says, and if you're following along in the book, that it would take great experimentation to figure out what this surface is. And so that might be some of your harder tasks on your homework. But luckily for you guys, we will eliminate the experimentation and just show you how this would work. Okay, so let's try to remember that x squared plus y squared plus z squared is equal to r squared. Okay, well, x is equal to sine of u cosine v, y is equal to sine of u sine of v, and z is equal to cosine of u. So this would be, I don't want an equal sign there. This would be x squared sine squared u cosine squared v plus sine squared u sine squared v plus cosine squared u equals r squared. Let's notice that, let's see, this one here, they both have a sine squared u. So sine squared u times, and what we have left is this and this, cosine squared v plus sine squared v, nice, and then plus cosine squared u equals r squared. Well, this is just 1. Hopefully everyone knows that trig identity. So that leaves us with sine squared u plus cosine squared u equals r squared. Aha! 1 again. So you get r is 1. So what the heck? What surface has the equation r equals 1? Well, that would be a sphere. Okay, so if we wanted to sketch this graph, no, that would be the wrong way to write that, sorry. We would sketch something like that. And there we have a sphere with r equals 1. So now we have found two common geometric objects and very doable ways of representing those objects as parametric surfaces. Okay? Alright, so there's other ones we can figure out. Okay? So one really easy one is if the equation was one of, or something that could be represented as z equals f of x comma y. I believe these were the oids, if you remember your oid sheet. So if we look at z equals the square root of x squared plus y squared. Okay? Well, if you remember how we would do this, we would, to figure out in the first place what this thing would look like, we would change our value for z, and as z got bigger, you would be just having concentric circles that started at the origin, and as z got bigger, the circles would keep getting bigger. And so what this is an elliptic cone, okay? So that's what this was old school wise. Now, what we're learning here is that if you can write it as z equals a function of x and y, then its parametric equation is quite simple. R of x comma y. So here we're no longer using u and v. We're using x and y. Be okay with that. It's just a surface of two variables. And that's going to be, well, just let x equal u. Okay? So this is just going to be x. And then let y equal y, or y equal v. So that'll be y. And then here, let z equal f of x comma y. So it's just, and that would be the parametric surface equation for this elliptic cone. So you might be asking, well, this is so much cleaner and easier than that. Why would we ever want that? Why would we ever want a parametric surface? Well, because we were very limited with the calculus that we could do with our z, okay? So if you think about these line integrals that we've been doing, now we're going to be able to do surface integrals. But we can't do the surface integral if we haven't figured out a way to write our equation parametrically, and now these are parametric equations. The difference is they are parametric of two variables and not just one variable t. So that's just trying to help you guys understand what you're doing, okay? I think we've got one more fact in this video, and then we'll come back tomorrow with another video. So now we're going the other way. Write a set of parametric equations for the surface of revolution and then, let's see, we're going to start here at 1. And then as x grows, this is going to be, they refer to this as Gabriels Horn. So watch what happens. This happens, and that happens, and that happens. We have another little circle there. So it's like a horn, if you will. Okay? All right, well, let's say that these lines started by this parent function, f of x equal 1 over x. So hopefully you can kind of envision. Now remember, when we do surfaces of revolution, we're taking a function and revolving it around the axis that we choose. So this one, we are revolving it around the x-axis, okay? So those are the two pieces of information that you need. What this is telling you right here are the rules for the surfaces of revolution, okay? So our parametric equation for this function, let's just follow the steps. It says let x equal u. So x is going to be u. So we'll call this 1 over u. Hopefully that makes sense. Okay? We're revolving around the x-axis. So it looks like u is going from 1 to 10. Okay? And v is still going from 0 to 2 pi. This right here is 10. And this right here is 1. Okay? Okay, so to find our y function in our parametric surface, we're going to follow this right here. So we're going to call that 1 over u cosine of v. Okay? And then our z function is 1 over u sine of v. And you should take the time to plug these in as your bounds and plot that parametric surface on an algebra system like a CAD program, and you will indeed get Gabriels Horn. And hopefully you believe that that's true, because it is. That's how it works. So that's the end of the part 1 video. We broke this up because this is kind of a lengthy section. So tomorrow we come back and we figure out how to find tangent planes to these things. So that's certainly going to involve taking the derivative. And we're also going to find surface area of these things. 2 common little calculus problems. Have a great day. Boom! Leaf day! Boom!